Welcome to the second lecture of network synthesis. In this lecture, we are going to see how we can synthesize electrical networks containing specific elements. And what are those specific elements? We will see driving point LC emittance functions, then driving point RC and RL emittance functions. And you already know what is emittance function. Emittance is a combination of impedance and admittance. So both are collectively called emittance functions. So we are going to synthesize these networks, and we had already discussed about three forms in which we can synthesize our network. First technique was series, in which you will see that the network elements will be synthesizing in series. And this was also called Foster one form. The second was parallel. So in parallel form, we will see that the elements will be getting synthesized parallelly, and we call this form as Foster two form, second form, right? So in Foster one form, you will see that elements will get synthesized like this and so on. And in Foster two form, you will see elements will be getting synthesized like this and so on. And the third form was ladder form. And ladder formed form will be achieved using either Cauer 1 or Cauer, C-A-U-E-R, two forms. So this is actually the combination of series and parallel forms. And there is a method called continued fraction by which we will get these Cauer 1 and 2 forms. So these circuits will look like this. So there is series also and there is parallel also. The combination of series and parallel is called ladder network, right? So this is we are going to see in this lecture in detail. So our first type of circuit is LC circuits we will synthesize. And how will we synthesize it? We will be using these LC immittance functions. So any network function can be synthesized into any kind of circuit which may contain R, L, C or combination of them. So if any network function that satisfied certain criteria, so that when you synthesize it using any method using Foster or Cauer form, so if you get only L or C or the combination of L and C, then such functions are called LC emittance functions. So emittance means it can either be in the form of impedance or in the form of admittance. So let us first see the series synthesis of LC emittance functions. So can you tell me if we have a emittance function that is basically impedance function, so if you have a summation of many impedance function, will that be in series form? Or if you have the summation of many admittance function, will that give you a series form? So definitely you already know that if you have summation of individual impedances, they are going to come in series. And if you have a summation of individual admittances, they will form a parallel circuit. So definitely for our first case, let me call it series form. And you already know this kind of form is also called Foster one form. So series one form or the Foster one form is definitely going to be a impedance function ZS, and there is a standard form of this Foster one impedance function for LC networks, and I'm going to write it. So let me take a constant K naught upon S. I'm going to explain why I'm writing such individual components of this network. Just let me write it first. So this is the standard form of Foster one form for any LC function or LC network, right? So you know that for any LC network, you must get a combination of inductor and capacitor, right? There should not be any resistance. So if you see the first element, since this whole thing is representing an impedance, if you see the first element, what does this represent? This represent a capacitor or an inductor or a resistor? Definitely it is a capacitor because S is in the denominator. Similarly, if you see this second element, what would you get from it? If you put this nominator into denominator, let me do it right here. Let me take only this one component. So if you put this in the denominator, you will get S square upon 2kJs plus omega j square upon 2kJs. So we will get it as 1 upon S upon 2kj plus omega j square upon 2kJs. Now, since this whole thing is impedance, right? This thing is actually representing an impedance. So whatever is in the denominator of impedance, what does it represent? It represent admittance, like, right, in the denominator. So this you can call it as YA, and this you can call it as YB, right? So you see that in the denominator you have a combination of two admittances, and definitely if there is an S in the nominator of admittance, it will represent a capacitor because the inverse of YA or ZA will have the S in the denominator. So this represents a capacitor, and definitely this, since S is in the denominator of this admittance YB, this represent an inductor. And how will these inductor and capacitor will be placed in the circuit? Will they be in series or parallel? Since you have two admittances being added, YA and YB are, since here they are added, definitely this capacitor and this inductor should be in parallel. I think in the last lecture we have already discussed it. So even if this whole thing is going to be a parallel representation of circuits, which is a parallel combination of capacitor and inductor, this whole thing are going to be in series with these components in series, right? So now why have I taken a component like this? This is very easily understandable that this is capacitor. This definitely will represent an inductor. So why we have taken a combination like this? So the answer comes that for any given function, ZS, let it be a ratio of PS upon QS, where PS and QS are polynomials of S, right? So this PS and QS will have certain roots. I mean, the poles and zeros. So if you solve this QS, you will get the poles. The roots of QS will give you the poles, and the roots of PS will give you the zeros. I have already told you in the previous lecture, right? So if you draw these things on an S-plane, I have already told you in the last lecture what is an S-plane. So in an S-plane, if you want to represent an LC circuit, you already know that for inductor, what is the value of inductance? It is J XL, right? So J is an imaginary component. Now if you take capacitor, what is its value? Minus J upon, minus JXC. So you see that the impedance value of inductor and capacitor are always imaginary parts, like they are imaginary. So since these things, these ratios or whatever are these are representing these impedance values, and since these are all made up of inductors and capacitors, the roots of this function ZS must lie on this particular imaginary axis, right? In the imaginary axis of the S-plane. So if you have, suppose, a component like K0 upon S, like here in the first this first thing, if you want to find the pole of this, what is the value of pole? Pole is given by the roots of denominator, and what is the root of this? Since there is no other component, the S will be equal to 0, right? This will be the root. So the pole of this first component, which is k naught by s, will exactly lie on the j omega axis, but at the origin 0. Now if you see this component k infinite into s, you see that what will this component represent? Since there is no denominator is 1, you can say that this is a 0, and that also lies on the origin, right? And where is the origin? Origin is again at the j omega axis, right? So you can see that both these poles and zeros are lying on the origin itself, which itself is on the j omega axis. So this still will hold. But suppose if there is a pole or zero on the other areas of j omega axis, like if suppose it is at here j omega and minus j omega, so how will you represent this? So I've already told you that if there is a constant kj upon s square plus omega square, so what will be the root of this particular function? Can you tell me what will be the root of this function? uh, it the root of this denominator, or the poles of this function, will be s is equal to plus minus j omega, right? So if you want to represent all the portions of j omega axis um, in the LC function, so you will have to take this component. You will have to take this component. So you will have to take this component. You will have to take this function, and you also have to take this function, so that you will be able to represent all the possibilities which can be included in any LC emittance function, right? And why I am calling poles and zeros collectively, because if suppose this qs functions gives the poles for this zs function, what will happen to ys? Ys is just the reciprocal of zs na. So you can write it in the form of ps and qs as qs upon ps. So whatever is the pole of zs function will become the zero of ys function, or whatever is the zero of zs function will become the pole of ys function. So whatever is true for the poles, it has to be true for the zeros of any emittance function for the LC circuit or any other circuit, right? So let's move forward. Now coming back to this function, now you must be wondering, okay, sir, why have we only taken this term only one, this term only one, but here we are taking n number of terms of this particular thing. So I must tell you that initially I have told you that for stability, the poles and zeros on the j omega axis must be simple. They should not repeat. So you cannot take k upon s and other one is k dash upon s. So what will happen is there will be two poles on the origin, which is on the j omega axis, and your system become unstable. So that is why in the standard Foster form or series form, we will only be taking one such term and one such term, and then these terms can be different because you see that these omega j values are different. For j is equal to 1, this will be omega 1. For j is equal to 2, this will be omega 2, and all these things are different. If in any case, if this omega 1 and omega 2 or omega 1 or omega n becomes equal, your system become unstable and it cannot be realized. So coming back to the point, let us realize this circuit and see how these series form or Foster one form looks. So if you want to draw this first form, so obviously you will start from here. So what is this component? So this is definitely a capacitor, and what is the value of this capacitor? If you take this k naught down below, so you can multiply it like 1 upon k naught into s, right? So what you will get, a capacitor whose value is 1 upon k naught farad. Now I already told you that this function we can represent it as 1 upon s upon 2 kj plus omega j square upon 2 kjs. So we already know that this whole function is impedance function, so this will be admittance function. So what will this be? What since these are the combination of two admittances, ya and yb, so these are going to be in parallel, and definitely one function is going to be capacitor and another is going to be an inductor. So what will be the value of this? Since this is ya, what will be the value of za? Sorry, what will be the value of ZA? ZA will be 1 upon 2 kj into s, right? So I have taken just reverse of this function. So we will get this. So this is basically a capacitor whose value is 1 upon 2 kj. So since let's take j is equal to 1 for the first circuit. So we will have 1 upon 2 k1. Similarly, this function will represent an inductor and its inductance value will be definitely 2 k1 divided by omega 1 square. So this will be 2 k1 divided by omega 1 square. Similarly, you will, if you put j is equal to 2, 3 and 2n, finally you will get many components, total n components. And let us write the last component as well. So this will be 1 upon 2 kn, and this inductor value will be 2 kn divided by omega n square. And finally, in the last, what you have a k infinity s, which is basically an impedance. So it will be a inductor. So finally, you are going to get an inductor whose value is k infinite. Clear? So this is your driving point impedance function synthesized from this particular function. So now you will be wondering, how will we get this function? This ZS function, how will you get? So what will happen is you will be giving some function like a s cube plus b s square plus c divided by p s square plus qs plus c plus something d, and let me call it as ZS. So what you will have to do is you will have to do a partial fraction, right? So by doing partial fraction, you can change this circuit into the form of this. So you will have to bring this particular circuit in the form of this, and there are certain conditions for this particular function. If this function satisfied those conditions, only then you are going to get this particular form. So we will see this in example, and after converting your function into this form, we can draw circuit in the foster one form like this. So let us go and see the fostered second form or the parallel form. Now this is your foster second form. It is exactly similar to the foster one form, but this circuit is representing an admittance circuit, not the impedance circuit. So what is going to happen now? All these components will be added in parallel in place of in series addition that we did earlier. So since this is an admittance function, k naught upon s, what will this k naught upon s represent? Capacitor or inductor? Definitely inductor, because this is an admittance and its impedance function will have s in the numerator. So your first function will be an inductor, and what will its value will be? If you bring this k naught into denominator, you will get 1 upon k naught into s. So this inductor value will be 1 upon k naught farad. Now coming to the second part, this whole function can be represented as this: 1 upon s upon kj. I have taken this numerator into denominator, plus omega j square upon kjs, right? So since this whole function was admittance function, so these functions will represent impedance function, and let me call them ZA and let me call this ZB. So there is a summation of two impedance function, and how will they be represented if they are summation of two impedance function? Parallel or series? Definitely series, because this is a summation of two impedance functions. So what does this represent? Inductor or capacitor? Since S is in the numerator, it represents a inductor, and similarly this will represent a capacitor. So you are going to be finding a combination of inductor and capacitor in series, whose value is, what is the value of first one? This inductor, 1 upon k1. I am taking j as 1, right? And what will the value of this be? This is the capacitor. Its value will be k1 divided by omega 1 square. Similarly, you will have n number of components, and let me write the last one. The last one's value will be 1 upon kn, and this will be kn divided by omega n square. And finally, in the end, you have a component k infinite s. And since this is an admittance function, this will be representing a capacitor. So its value will be k infinite, right? So this whole function represent ys. So this is your Foster second form of the LC immittance function or admittance function. Now, in many competitive exams or even in the semester exams, this question often asked as to write the properties of driving point LC immittance functions. So if you go and see these functions, uh, let us take this, because since both ys and zs are having the same form, we can take any of the function. So if you see this function, you see that here, what does this represent? This represent a pole at origin, right? What does this represent? This represent a zero at origin, right? And if you see this function, what are the things that this represent? If you see the poles, s is equal to plus minus j omega. So you will see that the poles are lying on the j omega axis. And also, since there is a difference between the nominator degree and denominator degree, and what is the difference? It is a difference of 1, right? So there is a deficiency of 1 0 in the nominator of this function. So you can say that in this function, this one, there is a 0 which is lying at the infinity. And why is it so? We have already discussed in the previous lecture. So you can say, just by seeing this standard form of this Foster, is that of LC circuits, is that there must be either a pole or a 0 or both at the origin, and there must be either a pole or a 0 at the infinity also. And you will also see that all these poles and zeros are lying only on the j omega axis, and there cannot be repetition of poles or zeros at a single point on the j omega axis, obviously because of the stability issues. They also alternate. So if you just plot these things, if you just uh, plot these things, you will see there is a pole, and then you will find a 0, and then you will again find a pole, and so on. Similarly, in the down below also, you will see that these poles and zeros alternate on the j omega axis. Now you must be getting confused that sir, how is it possible that this pole and this 0 are at the same place on the origin? No, but when you this first equation, this second equation, and this third equation, when you collect all this equation into a single ys equation, you will find that all the poles and zeros will lie on the j omega axis and they will alternate, right? So this is how you will find the pattern of any LC immittance function on the S plane. So all the poles and zeros will be on the j omega axis, and they will alternate, and they will not repeat on a single point, so that the system remains stable. So what are the properties? The first property is definitely the poles and zeros are simple. Simple means they don't repeat and interlace or alternate on the j omega axis. And what is the second property? There must be either a pole or a 0 at the origin or at the infinity. We already told you that there must be either a pole or a 0 or both at the origin or at the infinity. And then all the other properties of the positive real function and Hurwitz will apply to the driving point LC immittance function also. So we have already read about the Hurwitz function and the positive real function. So all those rules will apply to this LC driving point immittance function also. So let's move further. Now let us take an example. Here we have an impedance function, and we have to synthesize the Foster 1 and second form. So before going to synthesize, let us see, just by seeing this function, which kind of circuit elements we are going to get. So the simplest way to see it is to just draw a S plane and see where the poles and zero lies. So this is the real axis and this is the imaginary axis. So if you draw, what are the poles? The first pole is s is equal to 0, since there is a s here. So the first pole will be lying here. And where will the second pole will be? S is equal to plus minus under root 3j. So you are going to have plus j root 3 and minus j under root 3. Now coming to the 0, where will our first 0 will be? It will definitely be s is equal to plus minus j under root 2. So under root 2 is less than under root 3. So we are going to get our 0 at plus j under root 2, and similarly minus j under root 2. And where we are going to get our second zeros? So this s is going to give us plus minus j2. So 2 is greater than root 3. So we will get plus j2, and here again minus j2. So if you see that there are poles and zeros which are alternating on j omega axis. This is j omega axis, this is the real axis of S plane, and you see they are all alternating. They are not like two poles are not in continuation. So if there is a pole, then you will have a 0, then pole, then 0, right? So they are alternating and they are simple, like there is no two poles or two zeros at the same place, and they are all on the j omega axis. So this is definitely going to be a LC. Now coming to the question, we have to synthesize using Foster 1 and Foster 2 form. So let's take the Foster 1 form first. In the Foster 1 form, which is going to be a series form, so we are definitely going to go with ZS function. So you don't have to worry about the previous standard function that you saw. All you have to do is a partial fraction. For any function you get in the question, all you have to do is partial fraction to synthesize into a network. So ZS is s square plus 2 into s square plus 4 divided by s into s square plus 3. So you see that the degree of nominator will be how much? What will be the maximum power in the nominator? S square into s square multiplied, it will be 4, s to the power 4, and here it will be s to the power 3. So definitely the nominator degree is more than denominator degree. And for the partial fraction, you should know that the denominator power should be more than the nominator power. I mean, the nominator power should be less than the denominator power. So we have to rearrange this function before we go for partial fraction. So we will get s to the power 4 plus 4 to 6 s square plus 8 divided by s cube plus 3s. So we have to rearrange this function into something where we take a particular component out, and we will get another a fraction where the denominator power is more than the nominator power. So I think we can easily rearrange it. Here you see that s cube plus 3s, and here you see that s to the power plus 6s is there. So if you take s common here, and here if you in place of 6s square, if you only take 3s square, so this 6s square can be written as 3s square plus 3s square, and this is already written as s to the power 4, and then this 8 will go here. So this whole thing, this whole nominator thing can be written like this. So you have actually you have divided it into two parts, the nominator. So what you can take is, you can take one s common from here. So if you take for this component s common, what you will get? S cube plus 3s. So you see that this s cube plus 3s exactly same as this part. So this whole thing can be written as s into s cube plus 3s plus 3s square plus 8 whole divided by s cube plus 3s. Also, since this is summation of two parts, we can actually divide this whole thing like this. So s cube plus 3s will come here, and here also s cube plus 3s. So you can actually completely cancel these things out, and you will get just one s here, and there is a fraction here, in which you see that the degree of nominator is actually less than the degree of denominator. So what you are getting as ZS is equal to S plus 3S square plus 8 divided by S cube plus 3S. So you already got your first component S. Since this is impedance function, this is going to be an inductor of 1 Henry. And now all we have to do is we have to take the partial fraction for this component. So let us go forward. Zs is equal to S plus, how to take partial fraction? Uh, Let me rewrite it into the another form, 3s square plus 8 divided by, let me take S again common, and you will be left with S square plus how much? 3. So if you want to take the partial fraction of this component, you can write it as A upon S plus Bs plus C upon S square plus 3. I hope you all know how to solve this. So how to calculate the partial fraction? Solving this, you will get A S square plus 3 plus B S square plus CS, and you have to equate it to the nominator of this part, which is 3s square plus 8. So you will get s square and a plus b, plus you will get 3a plus cs is equal to 3s square plus 8. So now what you have to do is you have to compare constant with constant, and then multiple of s with multiple of s, which is not here. So and multiple of s square with the multiple of s square. So what you are going to get is a plus b is equal to 3, and then 3a is equal to 8, and there is no s on the right hand side, so c is going to be equal to 0. So from here you get a is equal to 8 divided by 3, and if you put this here, you will get b is equal to 3 minus 8 divided by 3, which will equal to 1 upon 3. 9 minus 1 means 1. 9 minus 8 means 1 divided by 3. Okay. So since we have got the values of a and b and c, we can directly write this function now. Let me divide it. We will get Zs is equal to S plus, what is a? A is 8 divided by 3 divided by S, and what is b? It is 1 by 3. So 1 by 3 into S divided by S square plus 3. So let me rearrange it again. So you get S, uh, let me call it 8 upon 3s plus, let me take this denominator nominator into denominator. So what we will get? We will get 1 upon s will be divided, so it will be 3s plus 9 divided by s, and then finally this part s. So we finally got our Zs as this. So can you correlate this function with our standard model of the Foster-1 form? Yes, we can. So this is our Foster-1 form, which was having 1 by s component, then this component, and then finally this component. So the similar in the similar fashion we have got this. So now let us draw this. So we have a capacitor, which is whose value is 3 upon 8, and then we have a parallel combination of a capacitor and an inductor, one of which value, since this is admittance function, this represent a capacitor whose value is 3, and this represent an inductor whose value is 1 by 9. So 1 by 9, and finally we have an inductor whose value is 1 Henry. So this is 3 by 8 is farad, 3 farad, 1 by 9 Henry. So this is our impedance function Zs. So this is how you are going to calculate any function. You just have to know the mathematical rules, and you can just convert any immittance function in the Foster-1 form or Foster-2 form or Cauer-1 form or 2 form we will be seeing later. So let us now move to the Foster-2 form for the same question. So you already know that Zs is equal to S square plus 2 into s square plus 4 divided by s into s square plus 3. So if you want admittance function, what is admittance function? It is basically reciprocal of impedance function. So you will get s into s square plus 3 divided by s square plus 2 into s square plus 4. So now you see that the numerator has a degree less than the denominator, so we can directly take partial fraction of this particular function. So we can directly write as plus b divided by s square plus 2. I hope you all know the rules of partial fraction. And then cs plus d divided by s square plus 4. So if you solve all this, I'm just going to write directly the answers. Ys is equal to, we will get s square by 2, sorry, not square, s by 2 divided by s square plus 2 plus s by 2 divided by s square plus 4. So you can solve this partial fraction and check whether this value of a and c comes out to be 1 by 2 or not. So it will come. So you got this function ys. Let us rearrange it in this form. So we will get 1 upon 2s plus 4 upon s plus 1 upon 2s plus 8 upon s. So you got these two function of this ys, and you know that since this is whole thing is admittance function, so the denominator will be summation of impedance function za, zb, let me call this as zq and zp. So what you see is these are two elements which are in series with the other two elements zq, zp, which are also in series, and these combination of these two elements are going to be in parallel because this is the summation of two admittance function. So let us now draw. So we will finally get this first function is 2s za. So za is going to represent inductor of value 2, and zb is going to represent a capacitor of value 1 by 4. So you will have an inductor whose value will be 2 Henry, and then a capacitor whose value will be 1 by 4 farad. And again, the second part will also represent an inductor of 2 Henry and a capacitor of 1 by 8 farad. So it will be like this, 2 Henry and 1 by 8 farad. So this whole thing is representing your driving point admittance function. So this is how you represent your Foster 2.